Thank you very much, Jean-Baptiste and Christine, for the organization of this summer school. So maybe I will start by writing my... What? Okay. So my title is Fukaya categories associated to graded surfaces and general algebras. So my aim in this course is to present you a result by Haiden, Katzarkov, Kontsevich. From 2000, I think it's 14. So what they do is, so maybe I will start by just, so to graded surface, so I will explain you what I mean by a graded surface in a moment. So they associate a category the Fukaya category of this surface so they call it the partially wrapped Fukaya category. And they prove the following. So one can construct okay, maybe I should first fix, okay. In all my talk, I will work about the complex, the field of complex numbers. So one can construct a finite dimensional K algebra lambda such that this Fukaya category is equivalent to the bounded derived category of this algebra lambda. Yes. Okay, so my aim is to explain you the theorem and to explain you what I mean by all these words. So, and yeah, so maybe this algebra is what we call a gentle algebra. So just to come back to the title here, so I will explain also what I mean by a gentle algebra. So my plan for this course is the following. So today I will explain, I will speak a little bit about this category, but not as a category yet. So the category part will be tomorrow, but I will explain what I mean by graded surface and what are the objects in this category and what are the morphisms in this category. So tomorrow I will really speak about the structure of this category. So this category is constructed using A infinity categories. So I will speak about A infinity categories. And also from this A infinity structure, we can construct a triangulated structure. So this one is naturally triangulated category. So my aim tomorrow will be to explain what are these A infinity categories and how we can construct a triangulated category from a A infinity category. So it will be really the algebraic categorical part. And part 3 will be on applications and also explain why this theorem is really, really nice and really helpful on both sides. So here it's really an algebraic description of a category. And so this is really the representation theory side. And here, this is really the topological side. And I will try to explain how we can use both of the tools coming from representation theory and from topology to deduce things on the side. And it really goes both ways, so this is very nice. And maybe on Friday I will try to explain some generalization of this result. Okay, so now let me start with this notion of graded surface. So I will start. So what I mean by first S by a surface here, my surface will be a smooth compact oriented, and the orientation will be important, connected, I'm sure, smooth, compact, oriented, connected surface, maybe no, with non-empty boundary, okay, so let me draw something. So here is my surface S, and okay, and what I mean by M, so M is a finite set of what I will call marked points, but they won't be exactly points or marked segments. And I assume this set is finite, and I assume that these segments, they are marked, so they are on the boundary of S. And I will also assume something else. So it just for simplicity, it's not strictly necessary, but here in this talk I will assume this, such that there is at least one boundary, one marked point or on each boundary component. Okay. So let me draw. So in this example, so this is what I mean by boundary segment. So it's just some kind of something like this. So is that okay? Can you see the color? Yes. So they will play the role of not really of stops, like if you know a little bit about these Fukaya categories associated of the partially wrapped Fukaya category. So the stops will be something like this. But it just, okay. You think that each boundary component is a circle, and you have some boundary segments that are marked. And I also assume that, yes, if it's really a segment, so I don't mark the whole boundary component in green here. So now I want my surface to be graded. So what I mean by a grading on S, so it's the same as a line field on the surface. And this is a section of the projectivized tangent bundle. So, okay, this is just a continuous map from S to so I take so this is my tangent bundle of my surface, so recall that it's smooth. So I have this tangent bundle, and I just take the projectivized tangent bundle here, and I just want that, okay. So for each x in S, I want that, so you can think about eta of x to be a line in the tangent space of S on X. Okay, so first. So first remark, maybe I can state this as a property. So such a grading always exists because S has non-empty boundary. Okay, and this really comes from the following fact. So in fact, maybe it's good to mention it now because I will use it later. So in fact, since okay, I have my so maybe I will write the definition of this. So maybe I will write this as pairs, and I will denote by brackets the class on this projectivized tangent space of the vector v. So where x is in S and v is in Tx of x. Okay, so maybe I can just denote by pi the projection of this tangent space here, and so this is a circle bundle over the surface, and since there is some boundaries, this circle bundle is trivial. So, and in fact, the data of this eta is the same as the data of a trivialization of this circle bundle. So that is here I have a homeomorphism from S to so here maybe I will just denote I think about S1 as R over Z, and so this one I denote by psi eta, and okay, this is just the natural projection here, and here, so my section eta will correspond to the zero section of this trivial bundle. Okay. So in a moment you will understand what this notion of line field is called a grading. It may be strange to call it a grading, but we'll understand in a moment why it's really it's a good name, in fact. So now I will. So the objects in my category, in my Fukaya category, they will correspond to graded arc. So for this, I first need to define an arc. So an arc gamma on S. So it's a smooth immersion, and what I need, I want that its endpoint such that gamma 0 and gamma 1, they belong to the set of my marked points here in and I also, I want the rest of my curve to be outside of the boundary. And so maybe just a bit of vocabulary more. So gamma is called simple if gamma is injective. And also I will, gamma is a boundary arc if gamma is isotopic to a boundary segment. So let me explain you what a boundary segment is. So here is my boundary. I have some marked segments here. So this is M, and so this is a boundary segment. Okay, so by a boundary arc, I really mean something like this. So maybe I should be a bit more precise by what I mean by isotopic. So it's isotopic with respect to, so I'm not really completely fix the endpoint of my curve, but I want it to stay in M. But I can move it just in the same component of M. Okay. So this is really so this is regular homotopy. Yeah, well, maybe it's just okay.
So simple loop would also be allowed then, because I can move
yes.
it a little bit.
So you mean here?
So if gamma of 0 is equal to gamma of 1, it would violate your definition of the vector.
Yes. Well.
But I can move the points a little bit.
Yeah. Yes. So this. Okay. In fact, I won't consider this one. I mean, contractible. I won't. No. But if it's not contractible, it's allowed. So just. Okay. I'm just. So maybe I should have added non-contractible here, but I allow gamma 0 and gamma 1 to belong to the same part of M. So just okay, to be clear, maybe I draw again my picture. So here I have okay, so this would be a boundary arc. Then so this one, for instance, is allowed. So this is a simple arc. And I could also have some self-intersection. Okay, I'm not sure. Okay, this one is a non-simple arc. So now I can define what I mean by a graded arc. So here I only use S and M to define this notion of arc. Yeah, so maybe just before speaking about grading of arcs, so I take an arc, so I have my curve here from 0, 1 to S. And I deduce from this curve, I have two different curves in the projectivized tangent bundle. So I have the derivative of gamma. And I can also compose gamma with a line field. So I get another curve here. And they both satisfy that when I compose with pi on S, I have this will be gamma. So in fact, so I have my curve gamma, and so here is somehow, this is gamma, and I can take the pullback along gamma of the tangent bundle, and what I get is something like this. It's like a cylinder, and so this lies in this is in PTS, and here I have two curves. So the first one is really given by eta, and I will draw it like a straight line. So this is, and I have this the curve given by the tangent vector of gamma, and here I get something like this. I don't know yet. For instance, I can, yeah, so this would be my gamma dot. And the grading on this gamma will be an homotopy from the green curve to the blue curve. So a grading of gamma is a homotopy from to, so it's a homotopy among curves in the cylinder. So it's really a continuous map from 01 cross 01 to PTS, such that, so f of 0t is eta gamma of t, and f of 1t is gamma dot of t. And now, and if I take the projection here on S, pi of f of st is always gamma of t. So this is my grading, and now I will try to explain what the name is well chosen. So because now you can, what kind of conditions? Yes, it's more. Yeah, in practice, it's more. It's transverse to the boundary. Yeah, it's always transverse to the boundary.
Like for eta.
For eta.
So you don't want eta to be.
No. So in fact, this line field and this grading will. So this line field, in fact, allows me to sort of compute angles on the surface, because So let me just write what I want to write. So from this homotopy, so I mean maybe I rewrite it. So I have this F going to PTS, and recall that this PTS is just S times S1, and here I can take the covering of this, so this is just S times R, and I can lift this homotopy to a F tilde, and here, so and the lift is unique. Here what I have, so it's really to ST. It is sent to. So the first component is, of course, is gamma of t, and the second one is some angle that I will denote by theta s of t, and my condition is that the initial angle for s equals 0 is 0. So the picture is really that. So instead of considering this cylinder, you consider. So now you consider a plane, and so again I have my gamma like this, and above gamma I have. So this will be the plane. So this right, gamma times r somehow, and here is okay. Let me draw again this cylinder. Maybe I could do it better. Sorry, I didn't think about this enough. So maybe I draw my cylinder here, and so here I have my eta. Here I have my curve. And so, what is a homotopy from the green to the blue is really something like this. So maybe I could draw it like this. And if I go from here to here by just going up a little bit, then somehow I get my homotopy like this, for instance. And here. So here I will do okay, something like this. So now if I lift this on the plane, so my curve so this is 0, this is -1, and my homotopy is, so this will be this F tilde. So this is something like this. And what I can write, so here is like T and S, and okay, so here I have T, so this is theta 0 of T, so this is theta 1 of t. And yes, that's it, I guess. Okay. And I could have taken another homotopy, and then my picture would have become like this. So imagine that I would go first. Maybe I take another color. I could do something like this. Then my picture would be like this. So here is okay. I maybe something like this, and this would correspond to this homotopy. Okay, and so we are just grading is the data of such homotopy, but we say that definition. So two gradings and f prime on gamma are equivalent if they are homotopic. So with respect to these homotopies, and it's not very hard to check the following, that two gradings are homotopic if and only if theta 1 of 0 is the same as theta 1 of prime of 0. So that is here typically this, I mean, because of course here my homotopy, I could, it could do this or something. Okay, but these two homotopies, of course, they are not the same, but they are homotopic. But these two homotopies, of course, they are not. They are not the same. So that's why here and this, okay, so the homotopy class of a grading is just determined by the value of this angle, and the value of this angle is its value mod 2pi, sorry. Its value mod pi is already determined, or mod 1 maybe. I'm just writing on here. So it's just so then the corollary of this is that the equivalence class of a grading is determined by an integer. So you can really, also you can think about this as follows. So if you are on your, okay, maybe I have my, so I have my curve gamma here on the surface, and so here I have my tangent vector of gamma. Here I have the line corresponding to gamma of t. So this is eta of gamma of t. And the choice of a homotopy from the green to the blue is really the choice of an angle, but like not mod pi, just the choice of something like this. So this is okay. So now maybe I'll write a definition. What I mean.
You mean that the difference of two gradings is an integer. Not really, you can't really name it by an integer, can you?
Yes, it's not, but it's. I mean, you can take the integral part of this, and this will determine. So this. So you always have that theta 1 of 0 equals theta 1 prime of 0 mod 1. So if you know the integral part, you know the grading. But I agree also that if you have if you have two different gradings, then the difference between the two gradings is just an integer. Yes.
But I mean, does it make sense to say I take the gradient as the zero gradient?
No, it cannot be 0 because, well, I mean, this curve on the cylinder, they are not the same curve.
That's what I mean. So
So
you cannot say that.
it's determined by an integer. I didn't say it's an integer, but okay, maybe it's not very precise as a statement, but it just the difference between two grading. I mean, two grading are are equivalent if and only if the difference between theta 1 of 0 and theta prime 1 of 0 is 0. And you have, I mean, the set of homotopy classes of gradings is canonically in bijection with the integers. So maybe I should have said it like this.
Say that the test is prime or homotopy. Are you requiring that within the homotopy of each time, does like f sub p have to be a homotopy between gamma and or between gamma prime and beta gamma, or can you just go around the cylinder everyone?
No, sorry. Can you say it again?
Like f comma f prime just have to be homotopic as maps of this square. It's not like relative to anything.
I'm not sure to understand the question. Yeah, I'm sorry. Maybe you, I didn't understand the question. So maybe later. Yeah. Okay. So now I want to. So now that I have this corollary, I can sort of define the shift of a grading. So if f is a grading, I can define f shifted by 1 is the the equivalence class of okay is a grading defined by so that f shifted by 1 will be just you compose f with a -1 translation, so R where R is a generator of this pi 1 of S1. But so this will be typically, this is F shifted by 1. This orange homotopy. So I go just, I want this to be gamma t and theta 1 of t minus 1. Okay, so you can define
So in your
this.
picture, will you turn left or will you turn right?
I choose to turn counterclockwise,
That's
but I could have taken this homotopy, but this homotopy would have gone like this way. Don't.
No, if F is the one that goes like this, what is F1, F shifted by 1?
So here in this picture,
Yeah. Can you draw F? Can you draw F?
it will be. Then it. So since I'm going here, it will be just one turn. This would be F1. I just do. No, sorry. Okay. Just half a turn less.
But you didn't say again what was F?
So F, what? This one. It was a huge one, but it's just an example. So, okay, maybe maybe I draw it again. So here is.
Draw the simplest example.
Yes, maybe a simple example. So this is eta, and this is F, and F shifted by 1 will be then alpha turn less, so it's just, this is.
Very good. Thank you.
Okay. So now I can define so now I take a loop. So this is a loop, and I take again a smooth inversion. And now again I can, so when I have such a loop, I can lift it, I can lift this gamma dot, so that goes from S1 to PT1, and here I can lift it here to like this. So this is gamma tilde here. I can lift this curve into a curve like this, but in here maybe I may have that gamma dot of 0 may be different from gamma dot of 1, or they are not necessarily equal. So here it's really to t, I go to gamma t theta of t, and I define the winding number of gamma. So the winding number of gamma is defined by so this is theta 1 minus theta 0. And now maybe I just write a property. So we can also define the notion of graded for a loop, grading for a loop. So if gamma is a loop, so gamma is graded. No. So there exists f a grading on gamma if and only if its winding number if is 0. Okay, it's just that somehow you want this cylinder, you want to be able to glue this cylinder from here to here with the homotopy. And this winding number will tell you if this is possible to find a homotopy that glue well on the endpoints of this cylinder. Okay, so maybe the proof is an exercise. Okay, so these graded curves, they will be somehow, so you will see later how, but the objects of my category. And now I have only maybe 5 minutes to define you the morphism. So, but the morphism, it will be given by intersections of curves. And for this, I will need another notion, the notion of index between of an intersection of graded curves. So I'm lost in my paper. So now I take gamma 1 f1 and gamma 2 f2. So two graded curves. I don't know if they might be loops or arcs, and I assume that they intersect transversally on P. So P will be some gamma of T1 or gamma 2 of T2. And now I define the, so I take, okay, maybe I just draw a picture again. So my picture is really in P, or is in TP of S. So this is eta of P. Now I have, maybe I have gamma 1, which is like this. And I have a homotopy F1 going from eta of P to, so this is really F1 of blank T1 going from eta of P to gamma dot of P1. And I have also a homotopy, maybe I take another color. So here I have gamma 2, and I have another homotopy, for instance this one. So this is F2 blank T2. And I will compose this homotopy, but so if I want them to compose, I will just take here some kind of, so this homotopy is the shortest homotopy in the counterclockwise direction from gamma 1 to gamma 2. So I call it kappa. And now I define, I can, what I can do first, I go from eta of p to gamma 1, then I do kappa, and then I do f2 minus 1. So maybe my picture is not, okay, I can redraw it. This was my F2. So I go this way, and then I do the reverse of F2 of T2. So I define the index at P from gamma 1 to gamma 2 as this composition. So first I do this, then I do kappa, and then I do F2 T2 minus 1, and I get a path from eta of P to eta of P. So I get an integer. Okay. So this will denote this will be the index, and you can easily check that. So it's really you want to, yeah. So proposition. So just by doing this small picture, you can easily check that the index from gamma 1 to gamma 2 plus the index P at P from gamma 2 to gamma 1 is equal to 1. You can also check the following. So if you have several intersections that so here I have gamma 1, here I have gamma 2, here I have gamma 3, and gamma n. So yeah, if I have several curves that enclose n-gon, so it's I really need this to be a disk, then I have that the sum of the index, so at pi from gamma I to gamma I plus 1 is n minus 2. So here you want this to be a disk. So kappa is just so you go counterclockwise, the shortest path from gamma 1 to gamma 2 counterclockwise.
Shortest path counterclockwise.
Yes.
So that requires that they are not the same.
No, they intersect transversally, so they are not the same. Yeah. But yeah, you could.
Kappa is the shortest path.
Yeah.
Gamma 1 to gamma 2.
Yes. And now I will define also the intersection on the boundary, the index of an intersection on the boundary to end my talk. So if gamma 1 F1 and gamma 2 F2 are arcs, ending on the same marked segment, then we can define also the index from gamma 1 to gamma 2. Yes. Yes, it's a
value time 1.
yes, you're right. Yes, yeah, I should.
Then it's a plus.
And it's a plus. Well, maybe it's a minus. But yeah. Yes, it's at time 1. Yeah. So now I have. So I have my green marked point here, marked segment. And imagine that you have two curves. So one curve arriving here. So maybe. So I just turn. So these curves, so these arcs, they end at the same green segments. They don't intersect, so it's not really good to speak about the index. But what I can do is just I take a small curve like this, and I put a grading on this. So here is. And I define the index to be the index of gamma 1 to, no, of, so it's, I go from gamma 2, so here it's in P1 plus the index, no, minus the index at P2. Here is P2 of A gamma 2. Okay, I defined it like this, and it's not hard to check that it does not depend on A and on the grading F. Does not depend on A and F. Okay, so I will just, if I have 2 minutes more, I end up with an example, and so that would be a running example in my talk. So I take a disk with and as for eta, I take the horizontal line field. And now I have, here is gamma 1, here is gamma 2, here is gamma 3, here is gamma 4. And now I have to define my homotopies. So gamma 1 will be just the zero homotopy. So I just have to compare this to define the angle between this line and this line. So theta 1 is 0. Here, for theta gamma 2, okay, I number it the wrong way. Maybe I prefer like this. Okay. So this will be theta 4 then this is theta 3, and then this is theta 2. And so if I didn't do any mistake, I can compute the indices of all this intersection, and it will be 1, 1, minus 1, and sorry, it's 1. Okay. And so maybe I will end this so you can check that I didn't make a mistake. Okay, thank you.